All right, guys. So this is section 3.5. And in this section, we're going to look at exponential growth and decay models. So we've already looked at what exponentials and logarithmic functions look like. Specifically, we're going to be talking about exponentials here. We're going to be doing, as I said, looking at growth and decay. Obviously, we're going to be solving problems that involve those things. And near the end, we're going to do something called Newton's law of cooling, which is actually a pretty interesting application. So what do I mean when I say a growth or a decay model? Well, the most basic explanation or function for this is a naught or a zero e to the kt. So that's the form that we would see for either growth or decay. A naught is the initial value, or let's say population, if we're talking about a population. K is the growth or decay constant. So K can actually be positive or negative. T is the amount of time. And F of T is the population or the new value after some time T. So the first couple problems, we're just going to manipulate the equation a little bit, kind of get familiar with it. So here they give us an initial population. They give us the growth rate of that population, K, and they ask us for what is the projected population in the year 2022. So first off, our equation, f of t, we know has to be of the form a0 e to the kt. A0, right, it said was the initial population, so this is A0. And notice it says it's in millions, so we're going to leave it as a decimal, but when we get our new answer, we have to remember that's also in millions. So we plug in, A0 is 60.5, and then we have E and K is 0.0145 times T. So this is our function of T. This is set up now so that we can plug in T or any value T and find what the population would be in that year. Notice that because the first year is 2005, that is the year or T equals 0. So if we plug in T equals 0, right, let's see what happens. So f of 0 is 60.5 e to this exponent times 0. Any number times 0 is 0. So I get 60.5 e to the 0. E to the 0 power is 1. So I get 60.5. So that means that t equals 0 does indeed represent the year 2005. That means, however, that if I want to figure out 2022, I need to know how far is that compared to in time, right? I don't just plug in 2022. So instead, I need to subtract the two. So let's see, we need 5 to get to 2010, then another 12 to get to 22. So it looks like 17 years. So that is our t. So let's plug that into the function. So we have the function evaluated at 17. This is 60.5. Excuse me, not times 10, times e. Times e to the 0.0145 times 17. Obviously, I don't know those values off the top of my head, so I'm going to hop over and use the calculator. So I have 60.5 times, let's see. I guess here, okay, here we go. E, let's see, we had 0.0145 and then times 17 up there, right? Oops, I didn't like that. Nope, doesn't want me to put it up there. Okay, so I guess we have to do that first. So let's do 0.0145 times 17. And then we need to use that as our exponent. So 60.5 times e to the 0.2465. So looks like we get 77.4 if we round to the same decimal place as the previous answer that was given. So we'll come back here and we'll say 77.4. Now again, that's millions. Okay, so 77.4 million people. Okay. All right, so here's another example. Again, they give us the population that we start with in 2005, but then they give us our ending population, and they don't give us our growth rate. So instead, we have to calculate that this time. So let's just plug in to see what our function looks like. We'd have f of t, which is equal to 26.3 in this case. And that is the initial population, 32.1, e to the k. And for t, right, we're still going from 2005 to 2022. So the t is still 17. So I'll even go back here and put 17 back in. Okay. So this time we're trying to solve for the growth rate, which is not as trivial as the previous problem, but still not too bad. So I first need to isolate the exponential. So I'm going to divide by 32.1 on both sides. So I have 26.3 over 32.1 equals e to the 17k. To get rid of e, remember we have to take the natural log of both sides of the equation. So I have natural log now of this fraction equals natural log of e to the 17k. And because these are inverse functions, they cancel one another. And I just get 17k. So now it's pretty easy to get k from that. Right, I just need to divide by 17. So I have natural log 26.3 over 32.1, all divided by 17. Or if you want, you could put it out in front and make it 1/17 times that. Now, if you wanted the exact answer, this would be it. But as you saw in the previous example, we typically get k to, let's say, 4 decimal places. So let's hop over once again and see what this gives us. So I need the, let's see, I need a natural log. So let's find that first. Here's natural log. And then it was 26.3, I believe, by 32.1. Let me just double check that. Yep. And then the whole thing divided by 17. So to 4 decimal places, we have 0.0117 and actually negative. All right, so oops. Let's go back to Word. Here we are. So this is negative 0.0117. So for k up here, we're going to put negative 0.0117. Now notice that that is negative. So that means that this isn't actually a growth rate. It is actually a decay. Here's another example. This time they've given us the model. We don't have to create it. And they also tell us that T is specifically in hours, and P stands for the population of bacteria. They tell us they also know that when T is 5 hours, the population is 1,000. So that means that P of 5 has to equal 1,000. And we also know that P of T, or P of 5, is equal to 200 e to the k times t, and in this case, t is 5. So basically we just plug everything in. And again, you'll note that it says use the above information to compute the growth constant K. So in order to do this, same as before, I need to divide by 200, both sides. We can cancel out zeros for that. So we get 10 over 2, or 5, is equal to e to the k times 5. Again, take the natural log to get that power down. I'll just write it as 5k this time. And natural log and e cancel. And we get natural log of 5 is equal to 5k, or rather, k is 1/5 of the natural log of 5. Now we could leave it that way. Another thing we could do is we could do technically, right, natural log of 5 to the 1/5 if we really wanted. I'm going to go ahead and leave it here. And then I'm even going to go as far as to get an approximation for that. So we need, let's see, 1/5 or 0.2 times the natural log of 5. So 0.321, let's say 3219. Right, so we're going to say k equals 0.3219. So that was part A. Part B says find the population after 450 minutes. Now you have to be careful. You can't just plug in t equals 450, right? Because that is in minutes. We need hours. So we first have to convert that. So 450 minutes times, for every 1 hour, there is 60 minutes. So this isn't going to come out nicely, I don't think. Let's see, it might actually 45 or 450 divided by 60, 7.5, not too bad. Okay, so that is the t that we're using for part B. So 7.5, and I should write hours here. All right, so we just need to plug that into the model now. So P of t, right, was 200 E, and we have K now, which is 0.3219 times T. And because we have T now, we can go ahead and plug that in. So P of 7.5 hours is 200, oops, just 200, not 2000. E to the 0.3219 times 7.5. All right, so I'm going to go ahead and just calculate that off screen here real quick. I have full faith that you guys can type this into your calculator. I come up with 2,236. And let's see, do they tell us? They don't tell us what to round to. So let's go ahead and, because it's a bacteria, it's a living thing, let's just round to the closest whole number. Particularly if I ever get a percentage of something, I always round up because it's a living creature. But I believe in most cases in the text or in your homework, they're going to round down. So let's go with 2236 because it's closer to that. All right. The last part says find when the population will be at 1,500 or 1,500. So that is asking us, when does P of t equal 1,500? So that's a little bit different, right? This time we're taking this equation and we're setting it equal to 1,500 and solving for t. Now we've done this many times now, but we solve for k, but it's the same process. So I'm going to divide by 200. Again, the zeros go away. And if you want 15 halves, right, is 7.5. This is e to the 0.3219t. To get rid of e, we got to take natural log of both sides. Okay, over here they cancel. And then we have natural log of 7.5 equals 0.31, or sorry, 3219t. And so if we want t, then we just need to divide by that decimal. Natural log of 7.5 divided by 0.3219 is equal to t. Again, I'll do that off screen here. And even better if you want a really, really good solution, instead of 0.3219, you would plug in this. So I'll do both just to show you what the difference is, to see if it really matters in this case. So I did an approximation here. Let's cap it at 2 decimal places, so 6.26 hours. And if we use the actual value of k instead of the 0.3, we would have natural log of 7.5 divided by natural log of 5 over 5, which would really mean multiply by 5. So natural log 7.5 divided by natural log of 5 times 5. And I still get 6.26 when I round. The difference was for this one, I got 6.258. Or sorry, no, 2594 and then 2596. So in this case, not a big difference. So here's another example where they tell us the type of model, but they didn't plug everything in for us this time. So it says that A is the population in millions, T is years after 2003, and they tell us that the population in 2003 was 204.4 million. So that means that we get an ordered pair, right? We'd say that the T, this is going to be T and, let's see, because they use A, let's say A of T is our ordered pair. So for 2003 and 204.4 million, this is going to be T equals 0 and 204.4. They then go on to give us another ordered pair. They say in 2005, which is 2 years from that, we have 205.6. So we have 2 points that lie on this curve. Now, why is that important? Because it's going to allow us to solve for all of the pieces that we don't have. So it says, use the above information to find an exponential formula to represent the population T years after 2003. Okay. Now, if you're given the, what we would call the initial value, which is at T equals 0, use that one first. Don't try to plug the other one in, because you're going to run into a roadblock. So let's use that first point, right? We have A of T equals A naught e to the kt. I am letting T equal 0, and I'm letting A of 0 equal 204.4. Now, what you'll notice is that if that's at time T equals 0, using this type of model, right, e to the 0 is just going to turn out to be 1. And so we, right off the bat, get that A0 is equal to 204.4. So when I called it an initial value, it's because it actually is the initial population. So rewrite the equation with the new information. We know that A naught is 204.4. Okay. Now the second piece of information is when T is 2. So let's plug that in. So we have 204.4 e to the k times 2. And we know that this is equal to 205.6. Again, we've done this type of solution before. We just need to divide over that 204.4. Then I need the natural log of both sides to get rid of the exponential, and specifically the natural number e. Okay. And we said that that's going to cancel these and just leave me with 2k on this side and the natural log on this side. So the last thing I need to do is divide by 2, and that gives me k. So I just multiplied by a half, same thing as dividing by 2. You can choose to write it the other way if you prefer. And again, let's get an approximation for this. So I have 1/2 natural log 205.6 divided by 204.4, and then times 1/2, and I get k is approximately 0.0029. Let's go one more digit, 293. All right. So once I have that, I can rewrite my model again, plugging in that information. So now A of t is 204.4 e to this decimal for k times t. That is the answer to part A. It said come up with a model to support or to pick up the data that we've already used. So next, the problem asks, use your model to determine in what year the population of the country will be at 221 million. So we're solving for t. We're saying that A of t is 221. We know that much. We want to know what is t. Okay, divide by 204. It'll cancel over here if we divide it to the other side. Then it equals the exponential. Take the natural log of both sides. And I'm just going to skip one step here because we've done this multiple times. All right, I take the natural log of e. Over here, I just get the decimal times t. And finally, t is equal to the natural log of 221 over 204.4 divided by 0.00293. So let's get an approximation for that as well. Looks like we get 26 point, let's say 65. Now, what does that represent? So it says how many years right? And what year? T is in years. Will it be 221 million? Well, it takes 26.65 years, but it wants to know what is the year. So we need to add, right? So we can just go ahead and I would say round this to the nearest whole number first. Right, that's about 27. And we need to add 2003 to that because that was the year that we started with. So it looks like it'd be 2030 when the population is 221 million.